we now have the foundational information about the layers of HDMI, EDID, HDCP, TMDS, what each of those layers does for you. Even painted some pictures of what a problem with each of those may look like, right? EDID, video but no audio, or maybe even having a picture where you have it looks neon green, neon pink, or neon purple. That could be from the color spacing aspect of EDID. HDCP failure, like a static screen, if that display data channel has been corrupted due to noise in the environment, or even, sometimes you're, I guess the point is, HDMI never tells you straight up what the problem is. Okay, you have to be able to observe the problem and deduce which of those layers you need to fix, right? But there is one problem, and this is on the exam here later. There is one problem that sometimes tells you when it's an HDCP problem, and that's with Apple TV. You may see, for example, your display does not support HDCP. Please connect an HDCP supported monitor, or please use component video cables. Some sources may tell you, or the old Apple TVs used to do that. And so that's like the one and only time that I've ever encountered where it actually tells you what the problem is, HDCP. Now, Apple TV seems to be, as much as I love it, seems to be a little picky when it comes to that. I know for a fact that I got an HDCP system, everything's good. I've actually found out that sometimes your HDMI cables, the Apple TV just is saying, basically by swapping a cable, it resolves that issue. You go and use that cable on other sources and have no issues whatsoever. So it's kind of a head scratcher there, but these are the real world obstacles, and you know how to address them now. Now we have a solid layer, solid foundation, I should say, for interconnecting these components, extenders, switchers, distribution amplifiers, matrices, etc., and designing systems out of it, because in this world, in this industry, where key digital is involved, the world that you live, the world that we live, we have to put many of these pieces together and make them operate as one, make them move and dance as one, and you have to manage those signals, maybe extending those signals long distances. And back years ago, there were HDMI extenders, balance as they were called, because it took the balanced, unbalanced extension technology, and every manufacturer had their own, proprietary TMDS extension, TMDS extender, and they were extending TMDS, so we know about video and audio, and a lot of those were dual cat wires, you may recall, and typically one hole of those cat wires was dedicated to extending TMDS data as you can do even inside of an HDMI cable. So you see how all this technology kind of works together and the foundations. But then also the second cat wire was typically used for additional data like EDID and HDCP. But everybody had their own products, and some of those were better than others, but for the most part it was very hard to get that right, and a lot of products were really bad, and HDMI is just not a medium that has a high tolerance for mishandling. So it was not a reliable thing overall. And so take you back to years ago, 8 years ago or so, maybe 9, when HDBaseT came out. It's its own technology, HDBaseT. It comes from an Israeli chip manufacturer, Valens, and they actually, it's a technology that delivers what's called 5-play. 5-play, their platform said, we're going to do HDMI video and audio, network, IR RS-232 control, power over this HDBaseT, and USB. all over a single cat wire. And when that initial product came out, they were extending it at 100 meters. Okay, now that was 1080p at that time, but now it's 4K even, you can do 100 meters. And some revisions of that technology came out that maybe added or subtracted some of these features here to meet price points and whatnot. But that was the initial platform, and it worked, and it was great, and it was reliable. And so every company in the industry that's doing video management and signal management basically went over to using HDBaseT technology instead of their own proprietary at that time. And so it's very interesting technology, very reliable technology. And what they did was they actually acquired the intellectual property to 100BaseT networking, and they adjusted that for AV applications. So what they do is PAM16, pulse amplitude modulation, and it takes that traditional TMDS ones and zeros, and we could see the clocking interval, how often, how the new signal kind of regenerates, how often, the interval of timing for that. And it takes that 1 and 0 and it multiplies it so you have 16 different 1s and 0s, and they are all carried over different frequencies instead of just one 1 and 0. And if that severe electrical noise were to occur, and if it cuts through that 1 and 0, corrupts that data, you've got nothing. Well, pulse amplitude modulation, PAM16, enables it so that if that severe noise occurs, it likely will affect only a range of frequencies within that cable, not every frequency. So that's what makes it ultimately reliable, is having 16 different instances of the data to work with. And it even has a really brilliant feature, forward error correction, so that if certain data is corrupted, it can analyze the pixel before and the pixel after and estimate what the pixel in the middle that got lost mayhaps should look like. So it's really brilliant technology. And because of the packetization and depacketization, HDBaseT technology in itself had its own reclocking on the RX side. Now, Key Digital, of course, has always reclocked on the input side, on your transmit side. And so show of hands here, has this ever happened to you? Do you remember years ago the HDMI clock stretching problem? Well, first of all, what is clock stretching? I mentioned the clocking interval, and I mentioned pulse amplitude modulation, PAM16, I'll call it. That's a mouthful. PAM16, how it contributes to the reliability of HDBaseT. Well, how about what contributes to the distance that HDBaseT delivers? 100 meters is this clock stretching. So the clocking interval very fast on traditional TMDS, and you can see how wide the HDBaseT, how wide, how long, how longly stretched that clock is. And that's how you get that distance. By stretching the clock, you could go further. Now, has this ever happened to you? Sorry, talking myself in circles here. It's easy to do when you're the only one in the room. There were a plethora of cable boxes, set-top boxes, reintroduced into the market, which were repurposed. They were old component video cable boxes, and the boards were modified to add HDMI. And those boxes were so lousy, the output signal, that when you stretched it with HDBaseT, the resultant, the image was so bad that by stretching it at the receive side, that reclocking, the display could no longer tell what was a 1 and what was a 0. You just had a black image. And this was known in the industry as clock stretching problem, HDBaseT clock stretching problem. And various manufacturers had posted various white papers about it, so they're probably still online. But a really great thing happened at Key Digital. We received a phone call one day, and the caller said, hey, what do you guys do about HDMI clock stretching? I said, well, what do you mean? And they said, well, manufacturer, this other competitor, I won't name names, of course. Look, everybody has issues, and we've had our own issues, and we learn from it, right? Well, anyways, your competitor is saying that whenever I work with this cable box, I need to add a splitter in front of the transmitter because of a clock stretching problem, a splitter, or we would say a fixer, right? And it would have to reclock that signal on the front end in order to make it work. And the beautiful thing was, because we had already had TMDS reclocking as part of our full buffer technology suite, we were already doing the clock stretching, excuse me, the reclocking. And so when folks called and said, hey, what are you doing about clock stretching? We were not experiencing that problem because our extenders like our Cat HD 300 Lite, Cat HD 500 Pros, they were already reclocking on the front end. So the folks working with Key Digital's products were not experiencing that problem, and it was a very large problem in the industry for a while. Folks said add a distribution amp in the front end. We would say add a fixer, and so that we would still be able to sell products to those people that called us up and perhaps didn't even have a problem with the Key Digital product. So as great and as reliable as HDBaseT is, there were still, a new problem occurred. Every few years, it seems, in digital video, there's a new obstacle that we must overcome. And that new obstacle that presented itself recently, HDMI 2.0a, the new standard of HDMI, gave us not just resolution and frame rate and color depth, but added additional parameters to the video signal like chroma subsampling, HDR, okay? And those new parameters added on to an already extremely heavy signal took the existing 10G bandwidth of HDMI and now a new source that's just cranking, outputting everything at the highest level can have a content that results in 18 gigabits per second. And this created a huge problem. Why? HDBaseT, which everybody was using, and it's reliable and it's everywhere, HDBaseT itself was designed around the 10 gigabit per second bandwidth. And so your new sources, 4K, 60 frames per second, 444 chroma subsampling, they couldn't output that content and be extended over an HDBaseT. The pipe was too small for the data. And so now you've seen products, and of course HDBaseT themselves, a great organization. They're always updating and trying to present solutions for this problem and other problems, of course. But we at Key Digital had released, in response to that, our X444. So it's in the naming, extender 444 chroma subsampling, standard length and long length extenders that support signals of up to 18G. And how can we support and extend 18 gigabits per second signal? Well, you may recall on the fixer device, we had a toggle switch for 18G to 10G compression. And that is what we are doing. We are applying, so you have a 4K source outputting 18 gigabit per second signal, and we apply that compression in the transmitter so that the signal can be extended at 10.2 gigabits per second to accommodate the 10G pipe. And at the receiver, we decompress so that we are again sending a 18 gigabit per second signal to the display. So the display is going to see 4K, HDR, 444, etc. And it is what is called a VLC, visually lossless compression, that is applied. So this is the solution for extending 18G signals on HDBaseT. And let me tell you, we're going to start talking about compression when it comes time to discuss our AV over IP, for example. And compression is, for the last year, 2 years, now a very real part of video signal distribution, signal management. When you do AV over IP, if you have a source that is 10 gigabit per second 4K, or even 18G, some systems may support, but you're going over a 1G network switch, you're going to have a compression factor there of 18 to 1, right? And so AV over IP especially has compression it's applied, and even in the traditional realm of HDBaseT based systems, we're going to be encountering compression. And it's hard to say what exactly will happen, but I think that as new resolutions like 8K are introduced, and regardless of their practicality, you're going to be looking at a scenario where that original content is that is output on the HDMI must be compressed in order to be sent throughout the professional video, the integrated system there.